Hello, and welcome to the amazing world of B-hyve smart watering. Today, we're going to talk about how smart watering works. And by the time we're finished visiting together, you'll understand the B-hyve app, all of the features in it, and how those features can be controlled to deliver optimum watering for anybody's experience. I've got some handy signs that will help us walk through this presentation, and hopefully these will be helpful. We're taking some technical terms, but we're going to break them down in a way that should make them simple and straightforward, easy to understand, and you're going to be able to fine-tune the app for any customer by the time we're finished. Let's start with the concept of Evapo Transpiration, ET. This little O or 0 right here means that it's reference evapotranspiration. All that means is that some really smart scientists have taken medium length, slightly taller turf grass, all of the same height, and they've put a pan on a scale in that grass, and they've weighed it day after day. And what they've determined is that there are 4 variables that drive plant water use and tell you how much water that plant has actually used during the day. And those variables are sunshine. All right, as the sun shines on the soil, it causes photosynthesis, and the plant then uses water. Now that sun also heats up the soil. Hi there. and drives the temperature as well. And so another key driver of plant water use is the overall mean temperature for the day. Additionally, wind affects the amount of evapotranspiration or plant water use. All right? And then finally, the amount of humidity in the air, so water in the air. Those are the major factors that drive plant water use. Now, we have that reference crop, that ET small sub-zero, all right, that tells us how much water a reference crop is using, but we've got to make it specific for the crop that we're actually watering in our specific zone. And so scientists have done further studies, and what they've found is that different plants have different rates at which they use water. And they've done lots of studies, and they found out the coefficient or a factor to apply against that ET 0. They found out then a factor to apply to that makes that plant water use specific for that plant in the environment that it's in. And so, for instance, within the B-hyve app, if you were to select flowers or annuals, that would be a 0.8 coefficient or factor that would be applied to the ET0. In the case of lawn, depending on whether it's summer or, whether it's a warm season or a cool season variety, you'd find that that would be between a 0.7 and a 0.8 factor for the lawn that would then be applied to that ET to make it correct for the site. Now there's a further factor that we need to take into account, and that is the site-specific characteristics, specifically to how sun and shade affect that site. As a customer sets up a B-hyve, they may look at a certain part of the property and say, oh, there's shade on this side of the property, and it's creating a microclimate. And so we've given the customer the ability to go in and make an adjustment for that. If there's shade in that area, then that area is going to use less water because it's not receiving as much sunlight, and that will slow down the photosynthesis process and slow down the overall water use. However, it's very important that a customer be careful about whether or not that's understanding whether or not that's really a shady site, because later in the day, as the sun travels over, that site may in fact get lots of sun later in the day. And you see the sun's beating down over here in that western sun late in the afternoon. Even after the sun sets later in the day, that area may still be getting heat from that building. And so the customer should be very careful in adjusting sun shade, because each of those increments reduces the amount of water that that site will receive. And so my suggestion on adjusting sun and shade is to always wait until there's been some beehive watering experience in the area, observe the area, and if it's getting too much water, then adjust down that microclimate after the fact. So we've talked about the two variables, which are the plant-specific coefficient and then the microclimate coefficient, that are then applied to the total or the reference evapotranspiration to get to the actual plant water use for that area. And that is called then the ET of the landscape, and that is both plant-specific and it is site-specific for the sun and shade. Another important factor then is the root zone depth. And the root zone refers to, let me come around here and just show you, it's this profile in here. And different plants have different root zones that they achieve. In a really healthy grass, that root zone could be 6 inches to maybe even 12 inches in a certain type of grass that has deep rooting. And those roots then, it's called the active root zone, and the plant is able to absorb water from that root zone. Now if you take annuals, especially when you plant them, they'll tend to have these I just planted today, and they're just about that deep right now. And so that's the relevant root zone there. Any watering that I do beyond that root zone, okay, will result in water waste. And ultimately that will go, anything that goes below where the roots are is water that goes past where the active root zones can take it out, and it's water waste. All right, so that root zone is very important. In the beehive, that root zone is determined by the selection of plant type. And so when plant type is selected, not only does it give us that crop coefficient that we were talking about, our plant coefficient, it also tells us how deep that root zone is. Now, the amount of water that is contained within that root zone is called the available water. And when we say available water, I need to tell you a little bit about what that means. How's water in the root zone different than the available water in the root zone? Well, it's like this. So let's imagine that these steles are water molecules, right? And so that's water. And then the soil particle right here, it has properties, and the water has properties where together they create these weak bonds.
Oh, sorry, just in front?
Yeah.
I can just come right here. I couldn't get a really good view.
Perfect. Okay. Okay, how do you want me to start it out?
Can you just kind of hold it up in front, like maybe right there, so I can see them a little bit?
Okay.
There you go, that's perfect.
All right, so again, explaining the root zone. Let's assume that this right here is a soil particle, all right, and that the steles are water particles or water molecules. And you'll see that some of the water will hold on to, and it's a term that's called adhesion, will hold on to the soil really tightly. And then these others are free to be taken up by the roots of the plant. And so of course the roots do a thing called osmosis. Do you remember that from your science class, where the water then passes from a higher pressure to a lower pressure into the membrane and is taken up by the plant. Now, there's not enough pressure differential for a plant to be able to take this water up. And so this water, we're going to say, is not the available water, right? That water will be in the soil even after the plant can't take any more water up. The plant would wilt and die, and that water would still be there. This water that's left here is our available water. Got it? And the way that B-hyve calculates then how much water to allow the plant to use before it waters again is it allows half of the available water. So let me just show you here. So if I assume that I'm just going to allow the plant to take up half of these, then it's going to leave this amount of water still in the soil that the plant can use. All right, and then it's going to irrigate again to replace that amount of available water. And so that then represents the soil at its full capacity. And that's what B-hyve does. B-hyve lets it drop down to where half of that available water is used, and then it replaces that water through irrigation. The other thing that's really smart about B-hyve is not only does it take into account irrigation and plan and schedule for it, but it also factors in rainfall. And so that if rain were to have fallen before the irrigation event, B-hyve will check for that and say, okay, I don't need to irrigate the full amount to replenish the water that was taken out by the plant. I can count some of that in from rainfall and then just irrigate the rest of it. Now that's really smart. Let's see now if I can put these away somewhere here. There we are. They've clumped back together. We're in business. Okay, now we then discuss the concept of that allowable depletion. Okay, so the allowable depletion is my available water, all right, and then I let 50% of it as my normal target be removed from the available water by the plant before I irrigate again, after taking into account rainfall as well. And so this right here is a very important concept, which is management allowed depletion, meaning that the user can specify how much water can be depleted. If I specify a larger amount, so let's say it's typically set at 50% as a default, so if I specify that there can be 60% depletion, that allows 10% more of the water to be depleted before it irrigates again. So that makes the watering intervals longer. If I make it shorter, so let's say I take it to 40% allowable depletion, then it will have, the system will irrigate more frequently. And so those are the concepts of managing water moisture. Now, one more thing about the soil that's really important to understand is that the soil has a certain rate in which it can absorb water. Let's see if I have a pitcher here. I just happen to have a pitcher of water. And so this soil right here is a very loam-like soil. It's actually potting soil, but it has characteristics similar to loam. And you'll see that when I put water on it, now this is a very high rate that I'm applying this water, but do you see how that's soaked right in? Now if I were to pour the same water on a clay type soil that has a much lower intake rate, you'd see that if I poured this much water on suddenly, I would get a lot of puddling on it, and if I were on a slope, I would get runoff. So basic intake rate is the measurement that B-hyve uses to say how much water can that soil take in over any given point in time before that water will start to puddle on the top and run off. Now the runoff risk is increased, as I mentioned a moment ago, if there is slope. And so we apply a concept called allowable surface accumulation, which says that at different slopes, I'll allow a certain amount of water to accumulate on the top before it'll run off. So that water will basically hold to the top of the soil unless it's a steeper slope, at which case that will run off. So by adjusting this allowable surface accumulation, what the B-hyve then does is it breaks the run time. So let's say the total run time for this area is typically 20 minutes, but if the intake rate of the soil can't handle a 20-minute irrigation without creating runoff, it will break that into 2 10-minute times. And if it can't handle a 10-minute run time, it would break it into 3 6-minute and 33-second run times. And so those are how cycles are determined by a combination of how quickly and how easily water can get into the soil, the basic intake rate, and the allowable surface accumulation, which is slope dependent. So hopefully that's pretty easy to understand. So B-hyve can take into account how much water the soil holds, how fast it can take it in, and how much water it can hold on the surface depending on the slope that's in it. Now let's talk for a minute about the rate at which sprinklers apply water. And we've got some different types of sprinklers here. We've got this canister impact, we've got a gear drive rotor, we have a spray head. We have right here a micro bubbler. This right here is called an emitter. And then this is emitter tubing, where the emitters are actually built in to the tubing itself. And in this case, these are actually pressure compensating, meaning it's a very accurate flow that comes out of these emitters. Now, precipitation rate refers to in gallons per hour or in liters per hour, depending on what part of the world you're in, how much water is distributed from the sprinkler to a certain area of the ground. All right, and as you look at this, remember back to, well, think about pizzas. And as you make a pizza larger, you get lots more pizza, right? The same thing's true here, is that even though the flow rate of the sprinkler right here is high, and it's a big sprinkler, as similar for this one, they're both high flow rate, because they send that water over a very large distance, they actually have very low precipitation rates. So the actual inches per hour of precipitation or application that comes from these sprinklers is actually quite low. Typically, we'd see it could be as low as 0.15 in a full circle with a small volume nozzle, and maybe up to 1 GPM. We typically wouldn't see medium area rotors like this with application rates much higher than that. The spray head is interesting because it looks small, but because it distributes its area over a relatively small area, it actually has a higher precipitation rate typically than these larger rotors do. Typical application rates would be between 1.4 inches per hour and as high as 5 inches per hour in some of the smaller radius nozzle sizes. So there can be big variability. The variability that you see in the different types of sprinkler heads and the different type of nozzles is the reason why we highly recommend a catch cup test. The number one thing that customers can do to improve their watering experience is to perform a simple catch cup test. And the standards that are applied to auditors of irrigation systems say that lots of catch cups have to be used, and it's a process that homeowners may think, well, that's just not practical for me to put that many catch cups out of my yard. But the reality for precipitation rate is, with a few carefully placed catch cups in a lawn, the accuracy of the precipitation rate that B-hyve is using to calculate the run times for the sprinkler is dramatically improved. I believe that this is the number one way to improve B-hyve performance and to save customers water, to ensure that they're using the right amount to achieve their landscape goals. So I highly recommend, if a customer is ever having an issue with B-hyve, I highly recommend that they conduct a catch cup test. The catch cup tester instructions are very clear, and there's great videos on them. Catch cup tests can be used as well for drip. In the case of drip, rather than putting the sprinkler cups out, and of course with drip you're dripping onto the ground, and so what you actually do is you put an emitter or the micro bubbler over the cup, and then you input the volume into the B-hyve app, and the B-hyve app calculates the rate that is specific to drip irrigation. One more concept. So I mentioned before that allowable depletion, how much water we allow the plants to take out before we irrigate again after taking into account rainfall. That's management determined. This one is as well. This concept is called efficiency. And the idea of efficiency says that as I put sprinklers out in the yard, I'm very careful in the spacing. Let me give you a more detailed example of this here. So a typical spacing for this area would include a sprinkler here, 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 and here. I could additionally put one in the middle in a full pattern. And what you'll find is, because it's all of those patterns that are used, so let's say those are the spray heads, and the spray head would be doing a quarter pattern, but that quarter pattern is going to be in a circular, in this case a quarter circle position, and it's going to go out over here like this. All right, and then this one right here is going to go out over here like this. And so what you'll see is that there'll be areas in this that will be covered 2, 3, or 4 times by sprays from different parts of the zone. All right, and so the efficiency idea says that that's not all going to be perfectly uniform. It's going to be something less than perfect. Plus, I'm going to have wind that potentially is going to create some drift across that as well. Over time, I may have nozzles that get plugged slightly, and so this head, for instance, in this corner might not be putting out quite as much spray. And so I have to make an allowance for some amount of loss of efficiency that actually, of the water that actually gets to the roots versus the water that I actually have coming out of the sprinklers. And so my first step to get the very highest efficiency possible is to make sure I check all my heads, to make sure the spacing is consistent between them, to make sure that the nozzles are set upright, that they're spraying correctly, that they're not blocked, that they're not tipped. And once I have my equipment as good as it can be, then it allows me to raise my efficiency. As I raise the efficiency, it allows those run times to come down, and that results in additional water savings. The two then primary ways of changing the amount of water that is applied are changing the efficiency, and that's going to change the run times, and by changing the allowable depletion, and that's going to change the intervals or the time between watering. And then the final adjustment that we talked about that's important is the idea of, I'm just sorting through these here. Everybody just be patient. Probably want to edit this somewhere, Stephen. Sorry. Is then the allowable surface accumulation, which then allows the customer to adjust the number of cycles that are associated with each total run time. That's the number of start times that those run times are broken into. So those concepts of allowable surface accumulation, that has to do with cycles, allowable depletion, intervals, okay, and then efficiency, and that has to do with run times. Those are the fine-tuning that can be done to the system to adjust problems with how often the system goes on, how long it runs, or how many times it cycles for each zone. That is smart watering in a nutshell. My experience with B-hyve has been absolutely fantastic. And of course, you can tell by what I've described here is that I really understand how it works. But I will tell you that the principles and the science behind smart watering are very, very sound. And that with a little bit of time, a little bit of patience, understanding how the catch cups can improve, the understanding of the precipitation rate, then understanding how allowable depletion can help the intervals, understanding how efficiency can help the run times, and then understanding how adjusting the ASA, which is associated with the slope, can adjust the cycle times, you can achieve wonderful results and very, very high customer satisfaction. I encourage you to really make sure that you understand these principles, and that if and as you do that, I am absolutely confident that you'll be able to deliver a highly satisfying experience to customers. And they'll be able to enjoy B-hyve doing exactly what B-hyve says it will do, which is to deliver guilt-free green by providing absolutely optimum landscapes and at the same time minimizing the use of water. Again, thank you for what you do. All the best in your efforts to smart water with B-hyve and to help customers do that. Thank you.